Hi, good morning, everyone. So in today's webinar, we are going to demonstrate an app which is called TAQDIR. So this app was developed by our college, by our software engineer Trolley, and its main purpose is for the public to perform self-assessment for COVID-19. So a short introduction of myself. So I'm an associate professor in the division of ICT in the College of Science and Engineering. So for this project, I mainly work with our dean, Dr. Munir Hamdi, and also our software engineer, Anis Trodi, as I mentioned before. So this is the introduction. The main motivation is that how can the public easily assess risk of COVID-19? So there are some known symptoms of COVID-19, but those can be subjective. So the main symptoms are fever, coughing, shortness of breath. But for coughing, for example, there might be heavy smokers who cough regularly. So how do you know this is a new coughing condition rather than the regular cough? So another example is that when someone feels hot and he's outdoors or working, maybe in a construction site, or as someone who works on the road, like a security guard or traffic police, and so on. So how does he know that he's actually feeling a fever or he's just naturally hot? So the normal way is that you take some equipment, some machine to measure your body temperature. However, this is not always accessible to all the people at all times. You might have it at home, but not at work. So the third one is shortness of breath. So this again can be subjective. So some people feel shortness of breath all the time, and some people may have some chronic diseases that lead to such conditions. So how does a person know that this is actually shortness of breath caused by COVID-19 rather than by another condition? So there was a case in New York. There was a driver who got into a traffic accident. So because of the accident, he was sent to the hospital, and then someone did an X-ray exam on him, and only then they found that this person was infected COVID-19. So the person himself never suspected he had this disease because he probably has some other regular conditions which are similar to the symptoms here. But the X-ray image clearly shows that he has a lung condition. So these symptoms depends on people's perception, and also there are people who might be overly sensitive to those symptoms. So for example, some people constantly fear that they have fever, and whenever they slightly cough, for example, from smoke, which happened to me as well, then they will suspect that they got COVID-19. Okay, so and then start to worry and this and that. So our main hope is that we have an objective way so that the public, without much medical equipment, can make a quick self-assessment. Okay, so here is the main idea of the app. So basically, the app will alert the users of new symptoms which are related to COVID-19. So this app, because it doesn't use medical equipment, the result is not authoritative, which means it can only be a suggestion or some kind of alert. So you cannot really use this to diagnose disease, unlike what I did in the other webinar. So we have built an initial prototype, which was mainly done by our software engineer, Anis. So in order to use this mobile app, what the user does is that he opens this app, and then he lies down, and then he places the phone on his chest, or her chest. So and then he stays flat for 30 seconds, And after that, the app will show a notification. So currently it is a vibration event. And then after that, the user gets up and see the assessment results. So it's very easy to use. So you just take your phone and then put on your chest and lie down. And after 30 seconds, you feel a vibration, and then you get up and see the app. Okay. Currently the app measures two things only. So it measures the heart rate and also the respiratory rate. Okay, so only rate. So as we will discuss in future work, we may apply some more advanced AI techniques. But so far, we mainly use signal processing. So here we have two rates. In our jargon, these are called biomarkers. And from biomarkers, we could also track the user's normal conditions and then compare this with the usual conditions and see if the user has any new symptoms. Okay, today the agenda is that we have a 30 minutes webinar. The plan is that I will show a demo for the mobile app interface, and also will show a demo for the administration interface. So this is the backend. So I will explain to you why we have this interface soon. And also we have some discussions and future directions for research. So this is still ongoing work. So if you are interested in joining us, please contact us so that we can build something together. Okay, so the first is the demo for the mobile app. Because our engineer Anis cannot join us today due to some technical issue, so I will show you through a video. So this is a video. As you can see that it's a simulator recorded on the computer screen. On the left, you see some code. So these code are written in JavaScript. And now you see that the user opens the app, and then the user starts to take measurements. So now the measurements are simulated because this is running on the computer. So in the real world scenario, the user will put the phone on his chest, and it will record the real movement. So here you see there's no movement because this is simulated on the computer. In reality, it will show some pattern. And from that pattern, I have checked myself. It's not very easy for the human to see the respiratory rate and so on, but it's clear to the computer. So after this measurement, the user can choose whether or not to upload personal information to the server. So the personal information may contain name and also the detailed measurement. So here it shows the results. So it has the estimated heart rate and also estimated respiratory rate, which means respiratory rate means how often you breathe per minute. So if you breathe heavily, then that might be an indication for shortness of breath. Okay, so now let's come back to the slides. So as I mentioned, currently we measure heart rate and respiratory rate. The main technology is time series analysis and also signal processing. So this analysis is performed entirely on the mobile device. In other words, there's no communication whatsoever in this step to any outside computers or servers. So everything is done entirely on the computer, and therefore this doesn't review any personal information to any third party or to the developers. So in the next step, as I demonstrated before, the user can choose to upload some personal information, but this is entirely optional. Okay. So in the second part of this demo, I'm going to show you the administrative interface. So the administrative interface is a web page, basically. So this depends on what the user updates. So the user can report some of the following or all of them. For example, the user can report the assessment results, which contains the two rates. Okay, so one is respiratory rate, the other is the heart rate. So the idea is that if the heart rate is very high, then this might indicate fever, although this is not always the case. For example, the user might be excited, or the user might just finish a body exercise. So it's just an indication, but we cannot make a sure diagnosis based on that. So the respiratory rate is more intuitive. So if the user breathes heavily, then that may be an indication of shortness of breath. Okay, so in addition to this, the user can also send anonymized information, such as gender, age, and course location. Okay, so in our test interface, we also ask the user to put the name, but in the public release, we are going to remove that part of the interface. So only general demographic information such as gender, age, and course location. So we do not ask the user for any health-related information such as previous conditions and so on. Okay, and finally, we stress that the user chooses what to report. You may argue that even the gender and age are personal information. So for this part, we need to use some more advanced techniques for privacy protection, so that we ensure that with the gender, age, and course location, we cannot uniquely identify the user from this information. So the purpose of reporting this is twofold. So first of all, the server is a more powerful computer than the mobile device. So the mobile device, such as the iPhone, has some capabilities, especially the newer generations. So for example, now with the A13 chip, the iPhone contains an API called Core ML, and with Core ML, the developer is able to put inside the app a neural network model. And also, it's not limited to neural network model. You can have gradient boosting trees, random forest, and so on. And the phone can execute those in an efficient manner. So it's first very fast, and second, it doesn't cost too much battery life. But even so, the server is still a much stronger computer, so it can give you a more accurate analysis. So this can not only give you heart rate and respiratory rate, it can also analyze a pattern and also identify suspicious patterns for COVID-19. So the second purpose of reporting is that it gives some aggregate information to the developer, so that the developer has an overview about where the users are, and also so how many people actually have suspicious conditions. So it shows the distribution. So now let me switch back to the video. So this is the admin interface. As I showed you before, because this is the development version, so we also put first name and last name, but in the public version, those will be removed. So in this interface, we have those records, and those records you can download the measurements to your local machine, or you can perform further analysis here. So there is also a map interface. So the user may choose to enable location services, or to actually report this location back to the developer. So based on this location information, for example, here we show a dot. So this I'm not sure where it is, but we have a volunteer who input this location, and we also have a dot here, which means one of the test users have input a location here. I think this is near Education City. Okay, so we have also written a detailed document explaining the idea, the app, and the interface. So if you are interested, I can share, please contact me offline so that I can share you more information about this project. So there has been some public efforts to collect information from COVID-19 patients. But so far, we haven't seen a large database about coughing sounds from COVID-19. There has been some research activities, but none of them have led to publicly available data sets or models. So the main technology to analyze sound is through spectrogram analysis. So the first step is that we generate a spectrogram using fast Fourier transform. If you have human-related sounds, sometimes you also do MFCC extraction, and depending on how many MFCC factors you have different dimensions of your output. And after that, you end up with an image. So this transforms sound to an image. And since you have an image, you can apply standard convolutional neural networks to analyze spectrograms. So here, the main challenges are how do you perform data augmentations, for example, and how do you deal with relatively long sound. So for example, you have a sound which has relatively short, a few dimensions in the spectrogram dimension. So for example, if you do MFCC, it might be less than 100, but you have a very, very long time dimension, so you can have the sound for several minutes. To analyze such a picture, so you have a very, very long and thin strip. This requires some effort and tuning for the convolutional models. So this is all I have to show you today. So next we enter the Q&A session. So if you have a question, please type your question to the Q&A box, and I will see it from the box. Okay, so the first question I see here is what machine learning models we have used in the TAQDIR app. So as I mentioned before, the app mainly uses signal processing. So we have built our program based on the PyHealth package. So what that does is that it takes a time series signal. So as I mentioned before, I record the accelerometer readings. So the accelerometer has 3 axes, X, Y, and Z. So the Z axis is the height. Okay, so the X, Y is horizontal movement. So we mainly use vertical movement, and this has been shown to be best practice in works. So let's see if we have other questions. Since we still have some time here, so let me tell you a few things more about our project. If you are interested in our app, please contact me and I will share with you an internal prototype version as an APK file. So you can install this on your phone or tablet through the file. So we also have an iOS version, which is slightly behind that. So this is, again, published as a file. So to install this file on the iPhone, it takes more effort than the Android device. So you need to install a software such as a Cynthia Impactor. And after that, you can install the app as from a file. So we have also applied to register this app on Google Store and also Apple App Store. However, we got some issues because now COVID-19 is a sensitive topic, and both Apple App Store and Google Play try to discourage this type of apps because there are so many of them, and they don't want to mislead the users. So this means in our app we cannot mention COVID-19, and we have to improve. We have to modify the interface so that it looks like it's for another purpose. So for this reason, it is not publicly available yet. So another thing I would like to mention is that we have received a lot of interest from the volunteers. So as you see in this interface, we have 75 entries, and this video was recorded, I think, in early June. Sorry, not in the middle of June. So now I believe we have much more interest from our volunteers. So far, our volunteers are mainly involve our students and faculty in the college. And if you are interested, you can also contact us to become a volunteer so that we can use your data to help improve our model. So if you are interested in our app, please contact me and I will share with you an internal prototype version as an APK file. So you can install this on your phone or tablet through the file. So we also have an iOS version, which is slightly behind that. So this is again published as a file. So to install this file on the iPhone, it takes more effort than the Android device. So you need to install a software such as a Cynthia Impactor, and after that you can install the app as from a file. So we have also applied to register this app on Google Store and also Apple App Store. However, we got some issues because now COVID-19 is a sensitive topic, and both App Store and Google Play try to discourage this type of apps because there are so many of them, and they don't want to mislead the users. So this means in our app we cannot mention COVID-19, and we have to improve. We have to modify the interface so that it looks like it's for another purpose. So for this reason, it is not publicly available yet. So another thing I would like to mention is that we have received a lot of interest from the volunteers. So as you see in this interface, we have 75 entries, and this video was recorded, I think, in early June. Sorry, not in early, in the middle of June. So now I believe we have much more interest from our volunteers. So far, our volunteers are mainly involve our students and faculty in the college. And if you are interested, you can also contact us to become a volunteer so that we can use your data to help improve our model. So let me see if I have other questions in the Q&A box. Okay, so it seems like we still don't have any other questions. So let me tell you one other thing about this audio analysis. So I told you that the audio analysis will mainly be based on this spectrogram. So now let me show you an example of such spectrogram so that you have an understanding of it. So this image, for example, is a typical spectrogram. So this is from Wikipedia for spectrogram page. So as you see from a person, you don't see much, but from the computer, it is actually very clear what is going on. So here on the y-axis, you have frequency. On the x-axis, you have time. Okay. So as I mentioned before, for the frequency, you only care about a narrow frequency band because this is sound generated by a human. And you could also extract the MFCC features. So after that, you have less than 100 different values on the y-axis. However, on the x-axis, it could be very, very long. So it could be up to several minutes. So depending on how the data looks like. So here you see you have a color image. So the color here is artificial. Basically, it shows you the intensity of this value here. Okay, so at this time, in this frequency, how strong is the signal? So here, if you have a low value, then it's shown in a bluish color. If you have a high value, it's shown in the whitish color. Okay, but to the computer, there's just a single number rather than RGB channels as in the normal image. And also here, the number is arbitrary fraction number. It's not limited to the range of 0 to 255 as normal images are. And because of these reasons, analysis of such images is a little bit different from what you do normally with convolutional neural networks. And also it gives you some other challenges. For example, how do you perform data augmentation here? So obviously rotating this image doesn't make any sense, because then you are going to mess up with the frequency and the time. So what you can do is that you can make the sound shorter, and then you have to make sure you preserve the pitch while doing so. Okay, so there has been some standard packages for this. In general, this is less developed than computer vision, and it is a research topic we have been working on in the RRC project. Okay, so let me check the Q&A box one more time. Okay, so there is one question. So the question is, can you elaborate on the process of how sound are converted to images? Okay, so the sound is a frequency, sorry, the sound is a time series. So here is one example. A sound is like this. Okay, so at time 0, you have this number 0, and at time 1, you have another number, for example, again, similar to 0. So at this time step, you have a value which is like positive 0.2, and here you have negative 0.3, for example. So in other words, you have a one-dimensional time series data. Okay, so how does this correspond to real sound? Well, you can understand this as air movement. So if it is a positive value, then the air will move towards you. Okay, so for example, if it's a negative value, the air move away from you, something like this. Or you can think about this as the movement of the speaker membrane. So if it's positive, then the membrane it goes backwards. If it's negative, it goes forward, and so on. So this is very simple movement data. And how do we transform this into a picture like this? Well, the main difference is that this is one-dimensional data, and here we have two-dimensional data. So in other words, we generate more data values compared to our inputs. So how can this be done? Well, the standard way to do this is called time windows Fourier transform. Okay, so it's called SFFT, short windows Fourier transform. So what it does is that you apply a sliding window. So for example, I have a sliding window from this point to this point. Okay, so I have this small time series subsequence. And after that, I apply FFT analysis, and the FFT will output a bunch of numbers. So each of those numbers will be a frequency value. So that number will correspond to one vertical strip in your image. Okay, so if you do FFT for this box, then you end up with this column on your image. Okay, so then how do you generate the next column on your image? So what you do is that you slide that window. So now the window will cover this area. Okay, and then you generate again your FFT signals. Okay, so as you see here in the spectrogram, the data is highly redundant because in adjacent time steps, you will generate your sliding window will cover a lot of overlap in your original signal. For this reason, what you can do is that you can also have a hop value, which means when you slide the window, let's say before you are here, and the next time you don't slide by exactly one time step, you can slide by 10 time steps like this. So this way you can reduce the overlap between those time windows. And then, and as a result, you will have a picture which is narrower than your input. Okay, so you have less time steps than your input, while your analysis may still be accurate. So that's how you convert a sound signal to a picture. So it seems like I have no more questions in the Q&A box. So that will be the end of this webinar. So thanks for coming. So if you are interested in this research, please contact me and I will share with you the internal documents and also the app. Okay, thanks for coming, and I hope you have a healthy day and stay safe. Thank you.